Hello and welcome back. So to finish up this lesson, we're going to be talking about polar coordinates and kind of how they apply to vectors a little bit. We won't go too big and crazy into what a vector is today. We're going to be doing them later on, but I'm going to show you why they're good with trig. So polar coordinates is this idea of taking the x and y grid system that you're used to working with and changing it into angles and a radius. So radius would be how far away it is. So let's go ahead and switch over to the whiteboard. So let's say we have the points. Let's say they have this point right here. Let's say this point is at let's pick a random value. Pick 3, 4. So this point is 3 to the right and 4 up. So if we draw a line, actually here, let me draw a straight line. Make that a little bit better. Let's draw a straight line from here to here. Now, we're going to zoom in on this a little bit. So computer, enhance. Hold on, actually. Computer, enhance. So now that we've got the enhanced computer image, we zoomed in a little bit so that we could see it a little bit better. We can see that this sort of line that we've drawn creates a right angle between the x and y axis. So we know that we are 3 to the right. My goodness me, those are tiny. Those are tiny. Let's get this a little bigger. There we go. So we know we're 3 to the right and 4 up. So we've used a right triangle whose legs are length 3 and 4. We know at this point that the hypotenuse should be 5 at that point. Using the Pythagorean theorem, 3 squared plus 4 squared, so 3 squared is 9, plus 4 squared, so that'd be 16, so 9 plus 16 is 25. If 25 equals c squared, then, square root of 25 is 5. So our hypotenuse is going to be 5. So that means that we know the length of this here distance. So from 0, 0 to where this point is, that's going to be a distance of 5. Now, we also know that if we make this theta, we can go ahead and say, okay, so that would mean that, so let's say sine of theta, so sine of theta equals, so that would be opposite over hypotenuse, so that'd be 4 over 5. So this is the point where, normally we would stop because we know enough. However, there is a neat little thing that we can do here in order to make this into a different kind of format. So this coordinate pair over here, this is what we call a Cartesian coordinate pair, tells us how far to go right and how far to go up. So these are x values and y values. So another way we could describe this is we could say that, we're starting off on the x-axis and we go a certain amount of degrees up and we go 5 out in that direction. So the angle here, so if you need to figure out what theta is, you could do arc sine. So remember, arc sine is something we would plug into the calculator. But for right now, I'm going to go ahead and tell you. So arc sine of 4 over 5, that's going to be 53. So we got 53, right? Yeah, it'd be 53 degrees because it's got to be the bigger angle. So yeah. So we got 53 degrees. And so if we wanted to write this in a different format, we could write this in what's called a polar coordinate. So a polar coordinate, instead of being written in the traditional x and y, is written in the form r comma theta. So in this situation, instead of saying, hey, go this far right and this far up, what we're going to say is we're going to say go at this angle and go that far out. So we're going to go 5 out. So if we went 5 forward, we would be somewhere around right here. So we would have started here, and then we would follow our angle, that angle being a 53-degree angle, along that path up to where this point is. So this means if ever we need to make a polar coordinate point out of our Cartesian system, we could do x squared plus y squared square root. So that would be our r value. And then we can just do arc tan. So we can do arc tan. So arc tan, and since y is always the opposite and x is always the adjacent, so it's opposite over adjacent for tangent, so that'd be opposite over, oh, sorry, not the numbers. We don't want the numbers. We want the letters. So we'd have y over x. So we would be able to do this and get a polar coordinate for just about any Cartesian point that we have. So let's go ahead and practice this with a couple of points. So I'm going to lay the points out, and then we're going to plug them into that there formula. We're going to see how that turns out. So let's say now that we have the point, let's say we have the point square root of 3, comma 1. So square root of 3, comma 1. So that would mean my x is the square root of 3, my y is 1. So let's see. So r, so that'd be the square root of 3 square plus 1 square. And then we'll take the square root of that. So 3 square, that'd be 3. So square root of 3 square, that's 3. Plus 1 squared, that's 1. So that would be 3 plus 1, that's 4. Square root of 4 is 2. So we have positive 2 for our radius. So our radius would be 2. And then we got to do arctan. So arctan of y over x. So y in this case is 1, and x in this case is square root of 3. So we know that there's some theta out there. So there's some theta where the opposite value, so the opposite value is the y value, so that'd be 1. The adjacent value, that's the x value, so that would be the square root of 3. And we've seen this one before. We know this song and dance. So that would mean that this right there would be a 30-degree angle. So that's going to be 30 degrees because this special triangle is a 30, 60, 90 triangle. And since we know what the fraction is supposed to be, we just have to use the angle that gives us that. So that would be right there. So in order to translate, we just plug them into these formulas. And if you need to use a calculator in order to get arctan, that's okay. On your independent practice examples, they should be written in a way that you don't have to do that. But on the off chance that, there is one where you need to calculate it, or if you're just still kind of learning the inverse functions of arctan and arc cosine and arc sine, that is perfectly okay to go ahead and do that on a calculator. Most of the standardized tests you'll take, you'll have a calculator for. Your college professor might feel differently about it, but that is not something you necessarily have to have memorized today. It's just something you kind of start messing around with. So anyway, you're not going to have to memorize it for the purposes of this program. So anyway, back to our stuff. So that's how we go from a Cartesian coordinate to a polar coordinate. And then down here, these two functions tell you how to get back. So if you're given r, so that would be the first number, and you're given theta, you just plug those in to figure out what x and y are. So, if ever you're given a angle and the radius that you're going to, so like the length of it, then you're going to be able to figure it out that way. So cutting back real quick. So let's say we were given the polar coordinate grid. Let's say r is 5, and let's say theta is 53. I know we kind of did this example already, but now we're going backwards, so it is going to be slightly different. So by that logic, so here's x, here's y. So we're looking at a 53-degree angle, so that's about this much. It's a 53-degree angle. Has a certain height and certain width. My goodness, that 53 is very hard to see, and it doesn't look very good. So we're gonna erase it and fix it with something better. So let's get rid of that. Get out of here. You're a terrible 53. Let's go 53. There we go. Much better. We know that the hypotenuse is 5. So we know that r is 5. We know that theta is 53. So we know that x is supposed to be the hypotenuse times cosine of theta. You might be asking yourself, well, wait a minute. How the heck did we get that? Well, how do we get that from this triangle? Well, let's zoom in a little bit, and then we'll talk about how this triangle translates into that fraction. So let's enhance a little bit. Thank you, computer. Computer enhanced it for us. So now that we've got the enhanced stuff, let's see how this plays out. So we do our SOHCAHTOA stuff. So we know that sine of theta happens to be 53 degrees, not 50, 53 degrees. That is equal to the opposite side, so that'd be y over the hypotenuse, which in this case is 5. And we know that cosine of theta, so cosine of 53 degrees, is supposed to be equal to the adjacent side, so that's x divided by 5. So from here, we can use some simple algebra. So we multiply by 5 on both sides. So that'd be 5 sine of 53, which is our theta. That's going to equal y, and if we do the same thing down here with the x's, then we're going to have 5 times cosine of 53. That is going to give us the x value. So in this case, if we do 5 times cosine of 53 degrees, that is actually going to give us 3. So we know that the x value is going to be 3. And meanwhile, on the y side of things, if we do 5 times sine of 53 degrees, that is going to give us 4. So we know that this would be a 3, 4, 5 triangle based on the angles and what happens when we plug these in. So remember, x is always going to be r times cosine. Y is always going to be r times sine. So you get your x's by doing r cosine, your y's by doing r times sine. And of course, this is always of theta. Anytime I'm speaking about a trig function, if I don't say of theta or of the angle, you're supposed to assume that that angle is in there somewhere. Because you can't have a trig function without an angle, because you can't have a triangle without angles. And that's okay. That's what we're doing. So cutting back over here. So that's how we do polar coordinates. And so next up, we're going to talk about vectors in component form. So vectors are an interesting little thing. They have to have a magnitude and a direction. So in the previous example, we were talking about how a polar coordinate is just a direction with a length. Well, turns out that a direction with a length is the exact definition of a vector. So if we cut over back to the board and we go to draw a vector, that's not a very good grid. Hold on. There we go, much better. So let's say we have a vector, and this vector's length is, let's say this vector's length is 2. And let's say this vector has an angle of, let's say 30 degrees. So if it has an angle of 30 degrees, that means that we can construct a right triangle. And I think you can see where I'm going with this. Yeah, we're just going to make x and y. So now, since we know the radius and the angle, we know this is 2. We know that this is 30 degrees. Yep, we can go ahead and find x and y. Break it down into its components just by doing that same stuff we were before. So, 2 cosine of 30 degrees and 2 times sine of 30 degrees. That's a 3, brain. That's a 30 degrees. And that would give us the exact values. Now, if you remember this from special right triangles, you know that these values are going to wind up being, so for the cosine, that's the longer side, so it's going to be square root of 3. And for y, that's going to wind up being a 1. Because it's a special right triangle. Square root of 3, 1, 2 triangle. 30, 60, 90 triangle. However, we don't always have to do this whenever we are talking about vectors. Many vectors, in fact, will just straight up give you where they start and where they stop. So if it starts at 0, and it goes to 2, 3. So if the vector is moving from here to there, all we're really going to do is keep track of how far it moves. So it moves 2 to the right, and it moves 3 up. So let's say this thing is called v the vector. So v the vector has an x motion and it has a y motion. So the motion it moves on x is it moves 2 on x, and then it moves 3 on y. 2 to the right, 3 up. Pretty straightforward. But now, let's say that we're going to do something a little bit crazier. Let's say that, Mr. Updegrove is being strange. So he's going to throw us a weird example. Let's say we're at the point 4, 5. And we want to move way over here to the point 16, 7. Okay, so there is a straight line that runs straight from here to here. We're going to call this one u. So this is the vector u. And we need to describe the motion that the vector u is putting us through. So it still has an x component, still has a y component, but now we need to describe this over a much bigger distance. So the distance from 4 to 16, that x distance, is going to be 12, because 16 minus 4 is 12, so you know, do the bigger number minus the smaller number, and we get 12. So 12 is our x distance. It's how far we move on the x-axis. Meanwhile, on the y distance, we don't actually move that far. We only move 2, because we're moving up from 5 to 7. 7 minus 5 is 2. So our component form of this vector, where we're describing the x motion and the y motion, is going to be 12, comma 2. And the interesting thing about that is if we put that on 0, we could describe that same motion with u. As a matter of fact, u could be motion from anywhere as long as it moves 12 to the right and 2 up. So anywhere we could put this vector, it will do that for us. And this is one of the more useful aspects of vectors. Since it lets us describe motion, we can describe motion in all sorts of different places by using the same kind of vector. But that's more of a physics thing. We're just talking about math right now. So we're going to go ahead and go back. And then we're going to talk about vectors in polar form. So we've already gone a little bit back and forth between Cartesian form and polar form, so we're not going to do that for much longer. But we are going to do is we're going to look at what a polar form vector looks like in terms of, it'll give us the vector, and then we'll go to graph it ourselves. So let's go back to the board. And let's say we're given a new vector. So this is a polar vector. So polars are radius and then degrees. So let's say we got a radius of 3 and an angle of 45 degrees. So if I go and I draw my system, so this is the 0 angle. So I need to go 45 degrees up, and I need to draw a line that is 3 long. So the distance from here to here needs to be a length of 3. Now, you'll notice here that I am not actually drawing the x and y components. And that's because you don't have to draw the x and y components when you do a polar form vector. It's one of those things that can make polar form vectors a little bit easier to do as well, because if we know that we're moving this far, and we know we're moving that far, well, we have some idea of how these angles are going to interact, because I'll go this way, and then I'll go this way, and I'll wind up right here. Later on, when we do polar addition, we're going to do that in certain ways, but being able to look at vectors on top of each other allows us to understand, well, when I add these vectors, where am I going to end up? What does that total motion look like? And that's one of the nice things about how vectors work. But right now, when we're talking about a polar vector, all we really want to make sure is, okay, so the line is this long and at this angle. Great. So if we know that, we know how to plot the polar vector whichever way it's going from a starting point. And so, yeah, that's going to be it for polar vectors. I believe that's the end of this particular one. Yep, and that's going to be the end of this particular lesson. So I hope you guys enjoyed, and I will see you guys in the next one. Bye-bye.